So, Anna, when we hear tech breakthrough, everyone pictures that dramatic Eureka moment, right? Like a mad scientist shouting, "It's alive!" But with quantum computing, it feels different. It's not one huge, flashy event, is it?
Oh, Alex, you've totally nailed it. It's not that big eureka everyone's waiting for. What's actually happening is way more fascinating. We're seeing these incredibly precise small steps just happening all over the world, each one adding to this larger, clearer picture. And if you zoom out, there are these three big threads right now, all pulling us closer to genuinely practical quantum technologies.
Three big threads, huh? Okay, I'm intrigued. What's the first one that stands out?
So the first, it's silicon. Yeah, our good old friend. In Australia, Silicon Quantum Computing, SQC, recently ran Grover's algorithm, a cornerstone quantum search, with 98.87% fidelity. No error correction, just straight up accuracy. That's huge because silicon has decades of semiconductor experience. It means we might build powerful quantum chips with tools we already understand. It's a quiet power move, you know?
Wow, so silicon, that's like unexpectedly powerful. But what about if you don't even need exotic machines? I mean, is there a path that's less about the hardware and more about the smarts?
Oh, absolutely, Alex. And this is where it gets really, really interesting because it totally flips the script. While we're pushing hardware, in Poland, there's this startup, Quantums.io, and they've launched something called Velox Q1. It's a quantum-inspired algorithm, but here's the kicker. It doesn't need quantum hardware at all. It runs on standard computers.
Wait, so it runs on normal computers, but it's like quantum inspired? How does that even work?
Yeah, exactly. It manages to outperform many actual quantum annealers, especially in complex optimization problems. We're talking about handling up to 200 million binary variables. This isn't theoretical, you know? It's being used today in logistics, finance, energy. It's a huge reminder that quantum doesn't always mean super cold labs and exotic qubits. Sometimes it just means rethinking algorithms, letting software carry more of the weight. It's just brilliant, really, how they're pushing the boundaries without the physical limitations.
That's pretty mind-blowing, Anna. The idea that software can mimic quantum advantages. So we've got hardware evolving, software getting smarter. What happens when you, put them together? Is there a blend?
Oh, you're totally anticipating the third big thread, Alex. That's precisely where the magic is going to be for a lot of early wins. Back in the US, at Oak Ridge National Laboratory, they're really leaning into this pragmatic approach, combining classical and quantum systems into what they call hybrid architectures. They're working with quantum brilliance, exploring ways to directly embed quantum processors right into classical supercomputers.
So, like quantum chips inside supercomputers? That sounds incredibly powerful.
Exactly. It creates these really tight, efficient systems that can handle tasks neither could manage alone. The thing is, no one really expects quantum to totally replace classical computing. The real power, the magic, is in how they work together. These hybrid models could unlock early wins in supercritical areas like material science, AI development, and even climate modeling. And this is all happening long before we have those super robust fault-tolerant quantum machines. It's the smart way forward, I think.